Welcome to Pre-Calculus. Today we will investigate solving rational functions, focusing on algebraic strategies that can reduce a rational equation to a linear equation. We'll take a look at two examples. Our first rational equation is 1 over 3n plus n minus 5 over 6n squared equals 2n plus 3 over 3n squared. So I'm going to just consider that this is a rational equation because I have fractions added to fractions equaling fractions. And really my first strategy when I'm approaching any rational equation is to reduce it down so that it's no longer a fraction. And our go-to for that is really to create the least common denominator. And that's often a good thing to do for any rational equation as a first step. I want to create that LCD, the least common denominator. So a good way to do that is to pick up the factors that are already in each denominator and compare them to the denominators in the other fractions. So I'm going to pick up our three denominators here. I've got 3n. I've also got 6n squared. And I've got 3n squared. So as I investigate those three, really what I'm on the lookout, if it's possible, is to pick one that is already the least common denominator. And you'll note that it's that way because the other two can divide out of it. So looking at the three, the best candidate is this 6n squared. So I'm just going to check. If I can divide it by 3n, then I can know that 3n is part of that least common denominator. So 6n squared divided by 3n, that would reduce to just 2n. So that checks out. 3n is a factor in 6n squared. We'll do the same with 3n squared. If I try to divide it out, this would reduce to just 2, but it's a clean divide. So that confirms to me that 3n squared is also a factor of the denominator 6n squared. So that's going to be my least common denominator for all three, 6n squared. Now once I create that least common denominator, my second step is then to multiply each fraction by the LCD. Multiply each fraction by the LCD. Now our goal in doing this multiplication is really to reduce the fractions down to one single level so that they're no longer fractions. Let's do the multiplication. So I'm going to write 6n squared, and I'm going to multiply each term times the 6n squared. So that's times 1 over 3n plus 6n squared times this fraction n minus 5 over 6n squared. And that equals 6n squared times the fraction on the far side of the equal sign, 2n plus 3 over 3n squared. So what I'm looking for in those cancellations is really what's left in terms of factors. So for this first one, really I've already done the division here when I was creating the LCD. So 6n squared divided by 3n squared, I see is going to leave me 2n. So this first multiplication results in 2n times that already existing numerator 1. We'll keep going. So for my second fraction, 6n squared divided by itself cancels entirely, leaving no additional factors. So that's just going to be plus n minus 5. And then for my third fraction on the far side of the equal sign, 6n squared divided by 3n squared is going to reduce down to just 2. And again, I see that I'd already done that work when I was creating the LCD. So I'm going to put 2 times parentheses 2n plus 3. Notice what that's done to my equation. I no longer have any denominators, and what this is reduced down to, as implied by our title, is a linear equation. So we're looking at a linear equation. We should expect one solution. So let's simplify that. I'm just going to reduce all this down as much as I can. So I'm going to lose the parentheses there and multiply. So this is 2n plus n minus 5. On the far side, I want to distribute the 2 through the binomial 2n plus 3. So that's 4n plus 6. Got some like terms to combine there on the left. 2n plus n is 3n. And then I'll repeat this. Minus 5 equals 4n plus 6. And at that point, I can combine terms across the equal sign. So I see that I've got 3n and 4n. If I subtract 3n from itself, it'll cancel. And it'll also subtract from 4n. So that'll give me negative 5 equals 1n, or just n, plus 6. And to finalize this solution, I'd subtract 6 on the right. And I would get the final solution here, n equals negative 5 minus 6, or negative 11. I do have instructions here to make sure to remember to check for extraneous solutions. And really where I'm looking is if I plug negative 11 in either of these three denominators, I want to make sure that it doesn't create a 0 and make my equations undefined. But I'm in good luck because these are all multiplying. So 3 times negative 11 is negative 33. 6 times negative 11 squared is going to be a number. It's 121 times 6. So that would give us something over 600. In any case, it's not 0. And similarly, 3 times n squared, if I put in negative 11, 3 times negative 11 squared, that one would definitely be 363. So we're good. We checked for extraneous solutions and all is well. Let's take a look at a second example. Notice, because it reduced to a linear equation, we had one solution. That's what we can expect. So notice how this number 5 equation is different. I've got 2 over k squared minus k minus 20 plus 1 over k plus 4 equals 6 over k squared minus k minus 20. My goal again initially is to create a least common denominator. And this is slightly different because these are either trinomials or binomials. And so I need to think in terms of factors that are binomials, least common denominator. Now, as part of this task, one thing that we should do at the outset of any rational equation is I should factor any polynomials. So as I create my least common denominator, I'll help myself out a lot by factoring k squared minus k minus 20. So recall how we would factor that. I'm looking for two numbers that would multiply to this negative 20, the c term there. So what multiplies to negative 20 and at the same time adds up to negative 1, the b term. And so I see right away that that's going to be for us negative 5 and positive 4. So as a first step, I can rewrite this initial fraction as 2 over its factored form, k minus 5 times k plus 4. Now the reason we factor that is because it will help us to write our least common denominator. So I'm going to write the rest of the equation, 1 over k plus 4 equals 6 over the factored form k minus 5 times k plus 4. So notice we do have two occurrences of that k squared minus k minus 20. So their factorizations will be the same. Well, that tells me what my least common denominator is. I have a factor here in the middle, k plus 4, but notice in each of these others, I have k plus 4 and k minus 5. So the least common denominator would include any unique factor. So the ones that I'll include will be both k minus 5 and k plus 4. Now, once I decide on what my LCD or my least common denominator is, remember that second step, I want to multiply each fraction by the LCD. Multiply each fraction by the LCD. And the goal, again, just as in our first example, is to cancel any denominators so that all I'm left with is numerators. Well, let's make that change. So I've decided what my LCD is. So I'm going to multiply this first fraction by k minus 5 times k plus 4. And again, that fraction's 2 over that same pair of binomials, k minus 5 times k plus 4. Plus, I'll also multiply my second fraction by the same k minus 5, k plus 4. And that fraction was 1 over k plus 4 equals, and then a third multiplication times my LCD, my least common denominator, k minus 5 times k plus 4. And that would be times 6 over that same pair of binomials. So got it set up, and what we're ready to do now is, again, cancel. So I see in this first fraction, everything is going to cancel. I share both those factors in my multiplication and in my denominator. So all that's going to emerge from that fraction is the numerator 2. From my second fraction, I notice that only one of these factors is going to cancel, k plus 4. So what emerges from that fraction is the one factor from my LCD, k minus 5 times the numerator 1. And then for my final fraction on the right side of the equal sign, again, I see that I have identical two factors above and below. They both cancel and they leave numerator 6. At that point, I'm ready to reduce and solve. I can let that parentheses go since it's just being multiplied by 1. So this is now 2 plus k minus 5 equals 6. Combine my like terms, my 2 and my minus 5. So that's k minus 3 equals 6. And to solve for k, I would add 3 both sides. And I would get the solution k equals 6 plus 3, or 9. I'll box that. I do want to go back and make sure that it is not extraneous. So again, all I'm checking for extraneousness is if I plug it back in, I want to make sure it doesn't create a 0 in any denominator. So if I plug it back in to these two factors, 9 minus 5 is going to be 4. 9 plus 4 is 13. 4 times 13 is fine. That's a legitimate number other than 0. And I think we're good on the other factors because they are just the same, and we can endorse that solution. Thanks for joining for this investigation of solving rational equations that reduce to linear equations. I'll let you solve your own rational linear equations. Thanks for joining. See you soon.